Every observation humanity has ever made about the cosmos starts right here. Earth is our absolute fixed point of reference, and the core rule of making those observations is that light takes time to travel. When you point a telescope at the deep sky, you are actually looking backward in time. We know the universe is roughly 13.8 billion years old. That specific number creates a hard limit on how far back we can look. Light originating from the most distant regions of space simply hasn't had enough time to reach Earth yet. It is still in transit. While light travels toward us, the space it moves through is actively stretching. A photon leaving a distant galaxy 13 billion years ago has to cross space that is expanding behind it, pushing that galaxy even further away during the trip. This stretching effect expands our total sphere of visibility to a diameter of 93 billion light-years. Anything outside the sphere is causally disconnected from us. No signal, no light, and no physical interaction from beyond that wall can reach us. This boundary is a limit of information rather than a physical end to space. We occupy a pocket of visibility where the cosmic clock has allowed enough time for light to finally arrive. To figure out what actually lies past that horizon, cosmologists rely on mathematical prediction and the data we can collect locally. This heat map shows the cosmic microwave background, the oldest light in the universe. By measuring these temperature fluctuations across the sky, researchers check the geometry of space. The CMD data shows that on a grand scale, the universe lacks curvature. It is spatially flat. Astronomy also relies on the cosmological principle, the assumption that, broadly speaking, matter is distributed evenly throughout all of existence. If you combine a flat physical shape with an even distribution of matter, the result is a continuous, endless expanse of repeating cosmic webs and galaxies stretching far beyond our sight. A flat, infinite grid of matter is difficult for the human brain to accurately visualize, but the math points directly to it. There is a mathematical alternative. A universe can be geometrically flat, but still have a finite, measurable volume. Imagine taking a flat plane of space and connecting its opposite edges. You get a complex topology, a three-dimensional donut known as a torus. This shape holds a specific, measurable amount of space, yet completely lacks any physical borders or edges. In this model, if a traveler flew perfectly straight past our 93 billion light-year horizon, they would never hit a wall or run out of space. Their straight path wraps around the universe's geometry, creating a cosmic hall of mirrors that eventually brings them exactly back to their starting point. A third leading theory stops looking at the shape of our space and suggests the existence of completely isolated spatial realms. This is based on a concept called eternal inflation. It proposes that empty space is in a constant, endless state of rapid expansion. Under eternal inflation, our observable universe is a localized pocket, a bubble where explosive cosmic expansion randomly slowed down, allowing galaxies and stars to form. Countless other bubbles could exist alongside ours, permanently separated by vast oceans of empty space that are expanding too fast to ever cross. In these isolated realms, the constants of nature could vary, resulting in entirely different physical laws than the ones we observe here. If eternal inflation is correct, the billions of galaxies we observe are just a microscopic speck trapped inside a much larger cosmic foam. When we stand on Earth and gaze out into the local night sky, we are looking through a restricted window. We cannot physically verify which of these three theories is the true reality. Technological advancement cannot solve this problem. A telescope 1,000,000 times more powerful than what we have today still cannot pull data from a region that is causally disconnected from us. The speed of light is absolute. Cosmologists are forced to map the unseeable by substituting physical exploration with theoretical mathematics and the faint echoes of local data. The ultimate consequence of the horizon limit is that our understanding of the cosmos will always be censored by the laws of physics, keeping the definitive shape of reality locked away.